Assalamualaikum and good afternoon, everyone. We are Group 5, and today we will present our microprocessor system lab 2 project on question number 1. The group member of our project are, my name is Nora Zwatina Dira binti Maidwan. My matrix is 2024-698662. Together with Nur Aimin Syaira binti Abdul Malik, 2024-29620. And Nurul Faiza binti Abdul Rashid, 2024-425-766. These are the content of our presentation. First, we will explain the question and objective, followed by the flowchart, masking, result, discussion, and conclusion. On question number 1, it says, write and execute an assembly program that turns on LED R0 to LED R9 on one by one from LED R0 to LED R9 as running light. When the switch SW2 is pressed, next, when the switch SW4 is pressed, the LED 9 to LED R0 turn on one by one as running light.
Thank you, Azwa. Hi everyone, my name is Aimi and I will be continuing our presentation. Let's look at the core objective we aim to achieve. As shown on the slide, we have 3 primary objectives. First, we want to implement a memory map I/O system. What this basically means is that we are configuring our program so that our hardware component, specifically the switches and the LED, are tied to exact memory address. This let the CPU talk to the hardware easily using regular memory command, making the whole integration seamless. Next, a big part of this project is getting familiar with the Simulator online simulator. We choose this platform to write and test our assembly code. It really helps us to see what's happening behind the scene, like tracking register changes, debug our logic step by step, and seeing how hardware actually react in a virtual environment. And that brings us to our third objective, which is actually control this simulated hardware component. We don't just want to write a code and that's sit there. We want to see how it works. So our goal is to take a physical action like pressing a switch in the simulator and have instantly triggered a real-time visual change on the LED array. So how do we actually pull this off and meet all 3 objectives? We map everything out into a clear programming logic. So let's move to the next slide and I will walk you through our flowchart so we can see exactly how the data flows. Alright, looking at the flowchart, everything kicked off at the start block. Tying right back into our first objective, the very first thing the program does is load the LED and switch address. This tells the system exactly where the hardware lives in the memory. Right after that, it goes straight into red switch status, meaning it's constantly listening to see if a user is interacting with the switches. From there, we hit our main decision point, and the system branch out depending on what the user does. First, it checks is SW2 pressed. If the user press SW2, the answer is yes, the program move down, set the LED, and add a quick delay. We need that delay because the processor moves way too fast for the human eye. So the delay holds the frame so we can actually see the logical shift left pattern move across the LED. Then it hits the end. But what if the SW2 is not pressed? Then the logic move over to check the next condition. Is SW4 pressed? If that one is yes, it follow a very similar path. It set the LED, adds the delay, but this time it triggered a logical shift right pattern instead. After that display is done, it also wraps up at the end. Lastly, we have the shutdown path. If the condition route us to turn things off, the program hits turn off LED. It's follow the no path on the right side, bypass all the shifting animation completely, and goes straight down to safely close out the end block. To wrap things up, this flowchart gives us a perfect bird's eye view of how our code handles memory mapping to read input and drive the LED exactly how we want them to. That's all from me for this session.
Here we go. Next, we go to masking technique. Before checking the switch, we need to using the masking technique, where is the registered switch contain 10 bits from S0 until S9. For this question, we only need to open switch number 2 and switch number 4 be pressed. For switch number 2, when number 2 is set to 1, while all other bits will be a 0. Therefore, the hexadecimal value is 0x004. When number 4 is set to 1, while all the bits remain to 0, the hexa number will be 0x010. As you can see, at the equation given, on the LED, turn on from LED R0 to LED 9 on one by one as running light when the switch number 2 is pressed. Here is the masking technique where it shows when the LED 0 is turned on while the others is 0, the hexa value will get 0x001. Why? When the switch 4 is pressed, the LED 9 to LED 0 turn on one by one as running light. So I put there at the switch 4, switch 9 is I put the 1 and the others bits will be 0. So the value hexadecimal we get 0x200 and default is 0x000. For the running step, we go to coding method on CPU later. Here is the coding that we already make it, and I already put in the CPU later. On the next slide, we want to talk about explanation on the coding, which is at line number 4, where is LDR1 is equal to 0xFF20000, which is addressed on LED, where LDR0, which is 0xFF2000040, is registered on switch. For LDR6 in bracket R0, which is read card switch stage, where R0 stored in R6. Each bit represents a switch. On TST, R6 and BNL, which is hashtag 4 is a switch to TST. When TST, check if the switch 2 is on. If on, branch to LSL if left shift. If off, do nothing or stop loop. On move R5 hashtag 0, STRR5 in bracket R1 and B again, it turns off all the LEDs when write 0 to LED register, return to the main loop again. And at the left shift init station, where is move to hashtag 1, starts LED plating at position 0, which is binary is 00000001, which is LED 0 is on. And at the left shift loop, which is LRL, R2, R2, hashtag 1, the shift LED bit to the left, example movement, 0x001, 0x010, and 0x100. It creates running effect. At the CMPR2, hashtag 1024, it stops when the LED reaches the last position, which is LED 9. It prevents overload. And here I will show the device on display LED output. So we go to the compile and load. When the coding already compiled and succeeds, we go to step into. And we can see that at the R1, we already registered the value FF2000200. And at R0, we already put the address registered, which is FF20040. Next, we continue where we put the switch number 2 is on and we push the button continue, the LED
will be in right to the left.
is going to be at R7, which is 1 by 1.
Hi and Assalamualaikum. My name is Nurul Faiza binti Abdul Rashid. So I'm gonna present for the next part of the coding, which is for the switch 4. So for the line 29, this label marking the beginning of the LSR subroutine. For the line 13, the move instruction for loads the immediate decimal value, which is 512 into register 3, which is R3. Then for line 32, the STR instruction is takes the data currently inside R3, which is started from 512 and stored in register 1 R1. Next, for LSR R3 hashtag 1, this shift the binary bits inside R3 to the right 1 position and store the new value back in R3. After that, compare the current value in R3 with 0. Then if the comparison show R3 not equal to 0, the program jump back to LSR underscore loop. If R3 finally reach 0, the loop ends and it moves to the next line. For line 14, this load a hexadecimal value into register 7, which is 0 multiplied to 0000. This is for our countdown timer. Then for subs R7 #1, this subtract 1 from R7. The S at the end of the subs tell the CPU to update its condition flag based on the result. Lastly, once R7 hits 0, the loop break. This instruction tells the CPU to jump back to the address to store in the LR bag. So I already compiled my coding and I'm gonna demo for my LED. So turn on the switch 4 and then we press the step into. So the switch 4 is the LSR loop and then the LED will turn on and then the LED will light one by one. That's all. Thank you. So next for the discussion, the program use memory map input-output to communicate with LED and switch in CPU data. The LED register located at address 0xFF to 00000 and switch register located at 0xFF to 00040. Next, when switch 2 is pressed, the program execute the LSL, which is logical shift left operation. Then the running light move from LED R0 to LED R9 and produce left to right lining effect. So next, when the switch 4 is pressed, the program execute the LSR operation. The running light move from LED R9 to LED R0, so produce a right to left running light effect. So switch 2 or switch 4 is pressed, the program write 0 to the LED and to the LED register cause all LED to turn off. So all the LED will turn off. The delay subroutine include to slow down LED movement, so the running light can be clearly observed by the user. Thank you.
Alright, to wrap things up, let's take a look what we have achieved in this project. First off, we managed to successfully implement and test memory map I/O programming on the ARM v7 architecture. Everything was verified and worked smoothly using the CPU later simulator. The main goal here was to build a bidirectional running light application, and I'm happy to say it developed and operated exactly the way we intended. To make that happen, we used conditional branching instruction. This gave us control over the program flow, which is how we were able to change the directional of the LED movement on the fly. Lastly, to actually see it working comfortably, we implement software delay loops. This let us slow down and control the LED speed so it's completely visible to the eye rather than just flashing instantly. Thank you so much for listening.